Live?
Oh yeah.
I think we're live. Checking Sahil.
Yeah, we're like,
All right. Hello, everyone. Welcome to today's episode of Corecast. I am your host, Tim.
I'm Mikey.
and this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. So without further ado, let's get to it. So we've been talking a lot about information, error correcting codes, and a lot of analogies to computing and physics. And so I guess we wanted to touch upon this deep, intimate connection between information and space-time. Before we get to that, I guess Tim, can you give our audience at least a super brief, high-level summary of what information is and how physicists interpret information?
Yeah, so I think we all know that information is sort of the things that you see on the computer. Like if you were to run a program, you know that deep down in the hardware, there's going to be some register, some memory, or some CPUs there handling zeros and ones. And loosely speaking, these zeros and ones are the information that drive a computer forward. Now, what does that have to do with physics? For example, this is actually closely related to physics. In particle physics, for example, we have particles, and we have the particles come with certain information, right? Like how fast it's moving, how much momentum is moving. And in a very literal sense, the mathematics of modern particle physics sort of tells this picture that you can sort of imagine a registry all over the entire world, the entire space-time, and it's keeping track of things like how many particles is in this location, how much velocity, momentum, energy it's moving with. So, and if you think of physics as kind of a computer, physical laws are basically manipulation of these information, and they can change and modify over time. And so in that sense, yeah, physics and information is intimately related.
Gotcha. Anything you want to add to that, Mikey?
Yeah, I guess we even use similar language, right? Like when in computing, people often talk about like the so-called state of a computing system, right? And that's kind of like the configuration of memory and of the hard drive, and it's kind of like a snapshot of what information is currently being encoded at any moment in a computation. And in physics, we also talk about the idea of a state, and it's exactly what Tim mentioned. It's like distribution of particles and each of their energies and momentums. So the idea is that like if you know the state of a system, whether it be a physical system or a computing system, it's kind of like a snapshot of all the information that's encoded in that system.
Gotcha. And so I just want to, kind of make this a bit more concrete. See, when you say information encoded in a system, we're talking about when I think of information, I think of it in a classical computer as a bunch of ones and zeros stored somewhere. So is it the same exact thing, or are there some differences? Maybe we don't have to go in deep in the weeds on this one, but just at a high level. Mikey, question to you.
I'm not exactly sure, not being a computer scientist, in terms of like what exactly consists of a computational state in classical computers. But I can
Mhm.
tell you that from a physics perspective, the state of a system is exactly the number of particles, their distributions in space, and their momentum. And that's literally all you need to describe the so-called state of a physical system. If you know those things and you know the laws with
Mhm.
which this physical system evolves, then you know in principle everything there is to know. Um, okay, is there anything I'm missing in terms of in a computational state? Yeah, it's basically just ones and zeros, but
Yeah,
I
I
don't
would
know,
say
it's a lot more complicated.
I would say in quantum physics things could get a little different, but in essence it's not different. So in a computer memory chip, you can, for example, flip a zero into one by injecting some energy into it, right? Then like maybe a bit can turn from zero to one or one to zero, and computation is performed when that happens. In quantum physics, it's a little different because we're dealing with possibilities. But I think it's quite analogous. You can, if you inject some energy in the system, you can turn on the possibility of seeing a particle here. And these particle counters could be the basis of quantum bits, right? 0 and 1. Except the only difference is that in quantum information, we talk about possibilities. So it's not as clean cut as zeros or ones. Sometimes it's like linear combinations of them. It could be like, maybe you flip a switch. There's still a chance that it might be a zero. It might be a combination of zeros and ones. So it gets a little more sophisticated. But I think the essence is the idea. The essence of the idea is there.
Okay, that makes sense. So there's actually an audience question that is tied to what we're talking about, asking is energy information? Tim, I'll point this one to you.
I would say it's not exactly the same, but one of the crucial, interesting thing about energy, why do we even talk about energy? Is because energy is conserved, right? It's because when two particles come together, they can exchange energy and they can leave, and then the sum of the two energy remains unchanged, right? So, but then we now know that that's not always true, right? In cosmology, energy isn't necessarily conserved. So the concept of energy is well defined, but it's not like so sacred, right? So information is similar. You can argue that when two particle comes in, they exchange information, and then when they leave, that information gets transforms. But now we know that this information is conserved. It doesn't matter what system you're in, even if you're in cosmology. So in that sense, you can think of, when particles exchange energy, definitely information is exchanged. So in that sense, you can think of information as a more generalized form of energy, although they're not exactly the same. I'm sure you talk to a physicist, they'll tell you like no. But I think colloquially speaking, it's, information it's like a more generalized concept, I would say.
Okay, I guess so. You're saying there's certain cases where energy may not be conserved, but we know from quantum physics that that information is conserved. Am I understanding that correctly?
At least that's a hypothesis. That I think a lot of physicists will believe that is one of the most sacred laws. We have not seen examples that information can be destroyed or created yet.
I think it's worth noting, though, that the non-conservation of energy, this is like very much like an edge case. In any kind of a closed system, in any kind of a closed box, energy is conserved and information is conserved, and there is a strong equivalence between the two. I don't know if I'd say that like the non-conservation of energy in cosmology is like, I mean, that's like it's like people were, it's shocking that it's not in some sense, and this is kind of a goal that we want to like try to understand this.
Yeah, that makes sense. I guess like so one so I just want to make sure I understand what both of you are saying, kind of condense it down. So what you're saying is that if you take any system, at least classically, it can be represented by number of particles, positions, and momentums, and then as long as you have, laws of physics that tell you how it evolves in the next state, you can perform a computation. The information itself would be like, I can then classically like ones and zeros, encapsulating the number of particles, the positions, and momentum. At least classically, is that correct?
Yeah, from the state of a system, as in like the species, distribution, and momentum of particles, you can compute both the energy and you can compute both the information of that state. And yeah, I guess information is in many ways more fundamental than energy, as Tim said. It's like a generalized version, but in a closed system, the two are pretty much equivalent.
Okay, so we've talked about this classically, which makes sense. How does this change quantum mechanically? Because I don't know what the positions and momentums of particles are, Heisenberg's uncertainty principle. So what do I change this with? Is there, I guess, Tim, maybe you were alluding to something, but I want to try not to go too much into the weeds with this one. So however high level you can get in the interest of time.
Yeah, I mean, I think information in that sense, like we mentioned many times, you can think of as the number of all the possibilities just sum to one. So for example, if a particle initially might have some speed, and there may be a range of possibility for speeds, right? And those possibilities, let's say there are 3 possibility different speeds, right? And then it's 33% each, right? They might have interacted with some other particle and escaped somewhere else, right?
Mm-hmm.
The speed of that particle or the energy or any other variable could change. But the fact that those 3 possibilities has to evolve into 3 possibilities, that fact remains, right? Logic dictates that, if 3 configuration can come in, there's gotta be 3 possibility it can come out, right? If I don't even know how to physically make sense if 3 possibility comes in, like only 2 possibility comes out. I mean, it's possible if 2 possibility merge, but there needs to be a lineage. Like you need to be able to follow these possibilities and track them. So I think that's the most intuitive way to think about quantum information. It's really the counting of the possibilities.
Okay, that I buy that. That is that seems intuitive, at least to me. So okay, so that makes sense at a quantum mechanical level. Now I want to jump over to space time, and I guess, Mikey, to you, can you give our audience, like, a bird's eye view of like what space time is, maybe certain things people don't realize about space time, learning from like a high school physics class.
No, I think the high school picture of space-time is pretty apt for this discussion. Like, so when we think
Okay.
of space-time, right, we think of like a canvas, a canvas you can paint on. Like, space-time is the canvas on which events can take place. And I guess the most pertinent fact about space-time for this discussion is the fact that, or at least empty space-time, the way we think about it, has a property called smoothness, meaning that if I take my hand and move it around in space and time, I'm not going to encounter much resistance. I mean, obviously here there's like air molecules that are providing some resistance, but if my hand was in a vacuum, like a perfect vacuum, one property of space-time that's absolutely crucial for the universe to look the way it does is that it's smooth. It should be possible to traverse this space-time without encountering any resistance. That's, I guess, diametrically opposed to like imagining that there's an existence of like some wall where my hand tries to move across the space-time and it hits some obstruction like a wall. And with that region of space-time is not smooth. There's some different characteristic in one region and another that there is in another region, and that would prevent my hand from moving across it without any resistance. So I think that's basically the smoothness of space-time, the idea that objects can traverse space-time or empty space-time without any resistance is like one of the most crucial properties and fundamental properties about space-time from the perspective of physics.
Gotcha. Anything you want to add to that, Tim?
Yeah, I think a nice analogy is it's like in the holiday season you see these Christmas lights, right? Like you see these Christmas lights string along. But and sometimes these Christmas lights, they kind of show up nice pattern. It's like a TV, right? They show up like a shape that moves along, like maybe like a little wave that comes along, goes along those Christmas lights, and that's roughly how we think about particles in spacetime. Like the spacetime is filled with like these little Christmas lights in every location, and if there's a particle, it lights up, right? And we know that if my hand moves from the left to the right, it's almost like some Christmas lights lit up from the left, and smoothly some turn off and some new ones turn on. So it's moving, right? So this behavior, this ability to kind of coordinate one light bulb to the next to give you this pattern of things existing and moving, that's critical to the existence of spacetime, right? Like if what Mikey was saying, like imagine the Christmas lights is broken somewhere in the middle, and then the signals of the Christmas lights kind of break somewhere, well, my hand can't go through anymore. So the smoothness of spacetime is intimately linked to the fact that, hey, like the lights are strung together in this particular way.
And I mean, this of course ties to the notion of geometry through general relativity, right?
Yeah, and I
guess,
think
Tim.
Yeah, I think that's very much Einstein's picture. Einstein's theory of relativity is a very zoom out view of our universe. It says that these objects and due to their energy or momentum, it will cause curvature and stretching and ups and downs in this fabric of space-time. And as other objects also live on it, they will feel the ripples and shape of the fabric, and also as a result move. I mean, it's like this elegant dance on like a really smooth fabric. That's the zoom out view of relativity. But that this is, remember, this is in contrast of quantum physics. Quantum physics paints a picture where you zoom in, you zoom into the smallest, and you see that hey, space-time is kind of had this grainy, gritty characteristic. It's almost like they're like little registers in different spots in space-time, going on and off, on and off, on and off. And somehow these two ideas actually work together reasonably.
Wait, can you describe more of the graininess before we jump into that other point you mentioned about the connection between the two, which is essentially the whole crux of this episode. But what do you mean by graininess?
Yeah, the graininess. I mean, it's not literally when you zoom in, you see pixels, right? But we do know that, like for example, particles exist in terms of number of particles, right? You can grab an electron, but you can't grab half an electron. So there's some sort of discretization. It's not clear exactly how that works. Like, for example, the number of particles is discrete, and you can argue that the number of photons is also discrete. And if you put particles in a box, right, a rectangular box, the energies of these particles are also discrete. So that kind of tells you there's some roughness in space-time, but it's not clear exactly where that roughness comes from. But there definitely is some roughness.
I see. So what you're saying is in quantum mechanics, you observe discrete things, but in space-time, more general relativity, more zooming out, you see space-time as like continuous and continuously smooth. Am I understanding that correctly?
Yeah, I think that's true. Yeah, Mike,
Yeah.
I think
Okay.
that's true, right? Yeah, I think general relativity does not predict discreteness of our world. Smooth.
I assume you wouldn't be able to use continuous geometry if things were discrete to begin with. One question I have, kind of like playing a little bit of devil's advocate, I guess like what would it mean if like you could pull half an electron, or like you could pull any like fraction of a particle, or if half particles came in, like what would that mean to quantum mechanics? Tim, I'll point this question to you.
So this is speculative, but Mikey, I think it will screw everything up, because like if we have an electron, we can just lose half of it to some weird processes. Then like electrons would kind of lose its entity, its flavors as electrons.
Yeah, I mean, are we assuming that electrons are fundamental? I mean, I guess the obvious example when that could happen is if we somehow find out that the electron is made up of smaller particles, like let's say it's like a bound state of two other particles, then you could imagine grabbing half of it. But if we're talking about fundamental particles, then by definition, it doesn't make sense to talk about half of an entity.
Okay, that makes sense. I kind of want to just drill into that and not take that for granted. Okay, so now I think we've laid the groundwork of what information is, both classically and quantum mechanically, how it ties to physics, and then also we have laid the groundwork of what space-time is, its continuity, and it seems like these two things sort of oppose each other, but they work. They in fact work together. So I guess Tim, can you continue your explanation? You were talking about the graininess and the continuity, and then this Christmas light analogy. Can you go further with that and describe how these two
Like I
things
just
are
want to point
connected?
out that like these two
Yeah.
things they could oppose each other, right? Like there's no rule that says like Einstein's theory about smooth space-time. It says that space-time should be imagined as like a smooth fabric, and it gives the conditions on what can create like what's the word what's the opposite of smooth? It gives the
Rough.
condition on which you could like create kinks in the space-time, you would need like a huge amount of energy in one region. Einstein's theory says that energy in a certain region of space can cause curvature. So if I wanted to create like a violent kink in the space-time, I would need to concentrate a ton of energy in one space, in one region of space, and that would create like a kink or like a, some non-smooth region of space. And then we have this picture of quantum mechanics that kind of says that there's this kind of discretization of space and time, and somehow they have to agree with each other if both are correct, because we observe a consistent universe, and a consistent universe can't have two contradictory descriptions. So I guess that's kind of like the fundamental mystery here is like what property of quantum mechanics and what property of relativity enables a consistent description of the universe. It's like a kind of a I know I'm just like splitting hairs here, but I just think that's like an important point to make.
Yeah, absolutely. Tim, what do you want? How do you want to respond, or to either one of us?
Yeah, I mean, general relativity and quantum physics, they are approaching the problem from different angles, right? Like, general relativity, the equations are derived when zooming out. And the whole point of quantum physics is you zoom in. So of course, one might not expect that the perspectives will be the same. And indeed, we see different things, right? Like, general relativity is smooth. Quantum physics is kind of rough. It's got kinks and fluctuations. But at face value, if you just think about, let's say, TV, right? Like, if I watch TV, I see people moving. I don't see pixels. If I walk really close, I see little pixels, little lights coming on and off. So at face value, there doesn't seem to be a contradiction. Like, it doesn't seem crazy that, hey, if you zoom in, you get these Christmas-like picture of quantum information, and you zoom out, you see like a smooth universe. That doesn't seem crazy, right? So the naive view is that there isn't a contradiction in most cases. And indeed, that is true. In most cases, there isn't a contradiction. Only in extreme scenarios when you begin to see weird behaviors.
Actually, I like that
see.
analogy. It's kind of like when we look at TV, we see smooth pictures that appear to be evolving smoothly as a person moves from one end of the screen to the other. But then, you turn on, oh, shoot. I guess it's not even, but back in the day when you used to watch TV, you used to see like white noise when you're missing a frequency, and you'd see just the static. It's almost like that static is like kind of what quantum mechanics predicts about the universe, and this smooth picture of like people moving smoothly from one end of the screen to another is kind of what Einstein's theory predicts. And so it's kind of like a similar question, like how do you take this pixelated representation of a scene and go from white noise to like a smooth picture? That's kind of like, I think that's a good analogy for what physics is trying to do right now.
Yeah, I guess Tim, do you have any I guess insight into, like, for most situations, we'll talk. I mean, we'll briefly touch upon the extreme cases in a little bit, but for like most of the cases that we see in our day-to-day life, like why don't you see like space time as like I guess like a jumbled mess, or not jumbled mess, but like a discretized mess? Like, is it just, yeah, just yeah, want to leave that question for you.
Yeah, I think it's just that when you don't have a lot of energy in the system, then these extreme cases don't happen. Like, and we know that we're going to talk about it, that when you put too much energy in space-time, you make black holes, and those are problematic. But if you don't do that, the quantum, I guess, roughness can get averaged out. That's just basic statistics, right? If you take, like 10 trillion quantum information, gather them up, average them out, the results tend to be pretty smooth, like statistically, if they don't have any special correlation with one another. You can argue that it's just a theory of statistics, right? And our world is very, very large. So when you average these out, it's not surprising that we see a very smooth picture, right? Like, I think real life is a super high definition TV in some sense. So it's like, it's not crazy. So unless you like destroy the TV, or in some crazy scenarios, it's fine. That this picture of quantum physics and relativity playing along with one another is perfectly fine.
I I mean, so one kind of question, maybe going more into the realm of consciousness is like, could it be that we perceive smoothness of space-time because our brain is like correcting for like these errors, or are they too small, or what would you say to that?
Well, I think if there were errors, it's probably corrected way before it reaches our brain. So
Okay.
space time already has some mechanism for like at least making itself smooth, so that or creatures or objects existing in it experience a non-violent existence, like something
Mm.
that's not static, right? Like if the world is like static quantum bits, just going in and out, like that would be a terrible existence. We don't see that.
Yeah, I guess Mikey, do you want to add anything to that? Bringing this consciousness picture in.
Yeah, I don't know. I've got a. I'm of the mind that nothing that the human brain does really affects anything about the laws of physics. I know that Roger Penrose would disagree with that, but yeah, I don't know. What is? Yeah, I guess I'm more in favor of like non-anthropomorphic description. I don't know. I don't want to like belittle anyone's ideas about the role that consciousness might play in the laws of physics, but
Mhm.
I haven't seen anything uh, in my studies of physics to think that it
Yeah,
does.
I mean that's the mainstream view anyway. I think it's non-controversial mainstream view. It doesn't solve any problem if you involve consciousness. So why would you?
Fair, fair enough. Also, Mikey, I'd recommend seeing Max Tegmark's rebuttal to Roger Penrose's microtubule thing.
Oh no, I read it.
Yeah,
Yeah, yeah. I mean, well, he does a calculation that shows that like the length scale of neurons is just far too large to
yeah, yeah.
But yeah, I don't know if that's a strong rebuttal because I don't know if that's really what Roger Penrose meant by it. But yeah, I haven't looked into this in a while, so I'm not like totally opposed to the idea, but I just haven't seen anything super compelling to make me jump on board with it. Let's say.
Yeah, yeah, yeah. Well, okay. I don't want to derail this conversation about rebuttals to Roger Penrose argument about
A fun
consciousness and
tangent.
quantum mechanics. Yeah. Okay, so in the time that we have remaining, I want to briefly touch upon now the more extreme case that we've been talking about, i.e., black holes. So I guess, Mikey, since I've been very much, calling on Tim a lot, I'm going to start calling on you. So can you, I guess, like explain to us, maybe where, if there's a paradox that arises, or like how this extreme case kind of throws a wrench in things.
Um, does it throw a wrench in things? I mean, I guess the way it might throw a wrench in things is a little subtle. So I guess I can start the conversation by
Hmm.
just pointing out um, one aspect of quantum mechanics that could throw a wrench in this whole thing. So, uh, in quantum mechanics, when we think of like two particles and two closely, let's just for example, let's say we think of two particles and two uh, closely localized regions of space, like two particles right next to each other. These particles can either be correlated with each other, or they can just be totally random with respect to each other, right?
Hmm.
Um, Particles can be correlated or they can be uncorrelated. If you accept that, then and you take that one step further, you come to the inescapable conclusion that in order for space to be smooth, i.e., in order for my hand to be able to move from one region of space to another region of space, it requires that two um, closely localized regions of space are in fact correlated with each other.
Hmm.
Um, if I had, let's say, like I had a region of space, if I just imagine, let's just imagine space as like a line, right? And I
Hmm.
imagine a bunch of registers on this line, right? Uh, each neighboring register needs to be closely correlated with each other in order for my hand to move through that space smoothly. Um, if I have one region of space where all the registers are closely correlated with each other, and another region of space that where all the registers are closely correlated with each other, but there is some break here where there's just, I guess, put it this way: if my hand is moving through space and it counters a region of space where that region is completely random with respect to the region that it was originally in, that would
Hmm.
constitute an obstruction in that space, right? Like, let's just take energy, for example, since that was one of the questions that came up. Um, if I'm moving through a region of space where the energy is, let's say, close to zero,
Hmm.
that requires some correlation between the points in that region of space, right? If energy is zero here, it's zero here, it's zero here, it's zero here, those are correlations. If I encounter a region where the new region of space is completely uncorrelated with the region that my hand just came from, then the energy in that region could be just completely random in comparison to the region it just came from. So that's just one example. Like if I'm going through a region of space with like zero energy, and I encounter a region of space whose energy is just totally random, right? That would hurt. That would be a very energetic boundary, and I would get my hand would be burned trying to cross that region. So I guess this is the kind of thing that ties quantum mechanics to the idea of smoothness of space. In order for space to be smooth, neighboring points of space have to be closely correlated with each other.
Yeah, that is a great foreshadowing of what we'll talk about in another episode. But I guess Tim, do you want to add anything to that?
Yeah, and I think that the kicker is we know that, from Einstein's perspective, we know that space-time is smooth. And it also tells you that if space-time is smooth, that means that nearby points are correlated, and the technical word we use is entangled. They're entangled. Right?
Hmm.
That's the quantum mechanical version of that. Now, the conundrum is what happens when you cross into a black hole, basically. So if you're falling into a black hole, we believe that if Einstein was right, when you fall inside the event horizon of a black hole, you feel nothing. Because you don't know it's a black hole yet. It's just as if you're free falling. Like the fact that you pass the event horizon, the place of no return, is of no consequence. Because imagine you're in a spaceship, you close all the windows, you wouldn't feel anything. And Einstein's theory tells you that if you can't differentiate what you're seeing in your lab versus let's say you're just near some stars, the physics must be the same, right? So if you fall into a black hole, the feeling you get, the physics you get, is the same thing as if you're orbiting a very massive star. So that's a fact. So Einstein tells you that space is smooth, it's correlated. But you look at quantum physics, well, it can't be, it can't, there couldn't be a further contrast, right? Because you know that if an object crosses the event horizon, it will never return again. So all the
Hmm.
correlation must be erased. Like imagine we've always used this analogy. Like imagine if I committed a crime, I throw all the evidence in the black hole. No one can ever retrieve those evidence anymore. It's as if that information is lost. It's as if those correlations, those entanglements are destroyed, right? But the question is, well, Einstein says there's no destruction. Quantum mechanics seemingly tell you that there is a break, a destruction. So who is right? So that's lies at the heart of the paradox. Is space-time smooth or is it not smooth? Or is it relative? Or is it like what goes on there?
Gotcha. So, I mean, if I'm not mistaken, this is called the black hole information paradox, right?
Yeah, exactly. And to our audience, maybe it seems like this is unrelated to real life, but let me just tell you this. First of all, black holes exist. This is not science fantasy, right? Like we have even taken images of black holes. They are actually
Hmm.
part of reality. So it's almost eerily weird that these things exist and we don't understand how it works. And second of all, um, the physics governing black holes, we believe, also extend to other scenarios. For example, we mentioned many times that our universe is kind of like being inside a black hole because the universe is accelerating the expansion is accelerating, there are going to be objects that eventually we cannot feel anymore. So imagine, let's say I send a rocket. Let's say I send Sahil, you, to a rocket and accelerate really fast toward the direction of expansion of the universe. There will be one day in which we will lose you, Sahil, forever, because the distance between you and I will expand quicker than the speed of light. You know, it will get so, the expansion will become so fast that the speed at which you recede from us will be greater than the speed of light. That's almost kind of like tossing you, Sahil, into a black hole. Like, you're gone. But is your information gone? Is it not gone? Because you don't experience any break in space-time. Is the entanglement gone or not gone? So these are real questions, and it's not just to do with black holes. It has to do with the structure of space-time itself. Like, is it connected? Is it not connected? These are like very basic fundamental questions. So I guess we'll talk about that in next episode.
Yeah, this is a great place for us to I guess, like, you know, as our usual tradition, leave the audience with any words of wisdom. Actually, I have one question for either of you before we do that. I didn't see it; it just came in. It says, question is, the quantum state diagram Turing complete, the number of states are finite or infinite? I don't know if that question makes any sense to you, either of you, or if you're familiar with that.
I would say if you look at quantum mechanically, the number of state is probably infinite. But in a given region, it is not infinite, of course. But we believe the universe is infinite, then probably it will be infinite. But also, what does it mean to count the number of state? That's also is a conundrum. Do you count the states that have fallen into a black hole, or do you not? So these are very tricky questions. But I'm sorry that there is no good answer. It depends on how you count. It could be infinite or not infinite.
Yeah, I mean, I guess the simplest example, you can imagine a finite universe where the horizon has a finite distance, and then the number of states is finite. I believe Seth Lloyd did the computation of the number of states in the observable universe. I forget what the number is, but it is countable. And if the horizon is expanding, then basically the number of states that we're able to sample may not be constant. So it really depends on what you think is happening outside of the horizon. Do you think the universe just extends to infinity? In the past, we did a couple episodes about how there likely are no such thing as infinities in physics. So just piggybacking off that episode, I would say that the number of states is not infinite. It probably is a finite countable set of states, though astronomically large. But on top of that, we know that the horizon is finite, and we know that states of information can pass inside and outside of that horizon. So I'm not exactly sure what Turing completeness, what defines that, but I would put money on the fact that the number of states, possible states in the universe, is finite. But within our observable universe, it is changing as possibilities can move inside and outside.
All right. Well, so now comes the tradition of leaving the audience with any words of wisdom that that you've taken from information in space time. Maybe anything black holes have taught you.
Tim first.
Yeah, and I would say this is kind of interesting. Like when I first learned about physics, and especially learned about this Einstein's theory. I mean, we keep seeing these images of space time is fabric. It's a fabric, right? But the question is like, well, what makes up that fabric? And for the longest time during my studies, like there's basically is no answer, and or you might encounter articles or maybe this question may seem like stupid, right? Ridiculous. Like, why would you even ask this question? But it turns out that this basic observation is very fundamental, right? Like we're literally asking what makes up space-time, and I think a lot of times, you know, in physics, it's helpful to really ask these fundamental questions, even though sometimes they might seem dumb. But a lot of times they actually lead to really deep insights, at least when framed properly. And I think this is one of those instances. And the story is just there's so many pieces and insight that and the research still going on. So hopefully next episode we'll uncover some more of that.
Who thinks that that's a dumb question? I don't know anyone. I don't know anyone that thinks that that's a dumb question.
No, I think if you talk to a physics professor, they might be like, well, what the heck does that mean, right?
Yeah, they would only say that because they don't know the answer and they don't want to feel stupid by saying that. But yeah, we think that the fabric of space-time is made of wormholes. So let me just leave it at that. Because I don't. Yeah.
All right. Well, yeah,
that's the next episode.
yeah, great way to end the episode. All right, everybody. We'll see you all next week. Thank you for joining us, and we'll talk about black hole information paradox next episode. So hope to see you there.